everyone, welcome to the continuing videos in the linear algebra series. So in this video we're going to be talking about just some more of the vector properties that we would have seen. So in a previous video we talked about adding, subtracting, scalar multiples, and we talked about, geometrically speaking, the concept of length and direction, although we didn't put an actual algebraic object to that. So that's what we're going to focus on here, but just to complete a bit of a picture, just to take a little bit of a look at just some of the properties that we have here. Now, you're probably not going to memorize these. In fact, these are probably properties you're going to use pretty much without thinking. Like eventually, we're going to say, if you want an example of using this one, you would probably, if you see 2 times a vector plus 3 times a vector, you're probably going to call it 5 times a vector without even thinking. So that would be using this 7th property that's been written down here. So for the most part, you're going to use these properties without thinking, but it is good to know that the properties we want to use without thinking are actually true. And you can take the algebraic ways of doing things and adding them to and using them together. For example, here, if we had u1, u2, u3 plus v1, v2, v3, we added them together. That's u1 plus v1, u2 plus v2, u3 plus v3, and we can change the order of addition because of course you can, it's addition. And we would get v plus u. So none of these properties are particularly complicated. They all come from the definition of how we added things together, so found negatives, all that kind of stuff back and when we defined addition, subtraction, etc. So none of these properties are particularly complicated, and hopefully they're not overly surprising either. So where we really want to go in this video is to talk about, some of the properties that we didn't mention, specifically what we're doing with the length, or in general, something called the norm. So the norm of a vector, so in 2 or 3D, we're really referring to as the length. Is going to be, and really we're just using the Pythagorean theorem. So if we think about what this would be, again, we'll stick in 2 dimensions. But let's say we had a vector whose component was v1, v2. And then we can just play a right triangle game. There's v1, there's v2, and then we just use our Pythagorean theorem. Here's the length of v. And we get the length of v is going to be the square root of v1 squared plus v2 squared. So that's what it's going to be in 2 dimensions, but the Pythagorean theorem, there's no reason to stop at 2. In general, we can go to however many components that we have. So in 2 dimensions, that would be the same as what we had written down. In 3 dimensions, it would be v1 squared plus v2 squared plus v3 squared. But in general, we can do this in n dimensions as well, because this is an algebraic statement, so even if we lose the geometry, the algebra part of it would still work. So we call this the norm of a vector. Again, referred to as the length, the magnitude, if we're talking about in 2 or 3 dimensions as well. So in terms of some properties, so for example, we had the length of the vector 1, 2, 3. That would be the square root. Actually, say 1, negative 2, 3. That's 1 squared. Be careful with your brackets. And we get the square root of 14. that's what the length of a vector would be. There's also stuff called the unit vectors. That's a vector of length 1. Or for higher order or higher dimensions, the norm is going to be equal to 1. So for example, 1/2 1 over root 2 and 1/2. Again, we could verify it, square all of them, add them together, and we get a length of 1. So, in terms of some properties of this, one thing to note about the length, which shouldn't be overly surprising, is that it's greater than or equal to 0. We're squaring a bunch of things, adding them together, taking the square root. Of course, it's going to be bigger than or equal to 0. But feel free to pause the video and ask yourself, when can it be equal to 0? So this equals 0 if and only if v is the 0 vector itself. So the only way it can actually equal to 0 is if we have the 0 vector. Everything else is going to be positive. The only chance it can equal 0 is if all v1, v2, v3, all the v's are equal to 0. Okay. So, once we've talked about lengths, we can talk about something called distance. So the distance from P to Q. So if we had 2 points, 2 dimensions, 3 dimensions, heck, it can be in 9 dimensions if we wanted to. We know from a previous video we could find the vector PQ. And so in general, we can also find the distance from P to Q. So the distance from, let's say, U to V, so if we called this thing U, we called this one V, the distance from U to V would be the length of PQ. In other words, V1 minus U1 squared all the way up the line. So this is something called the distance formula. You might have seen it with points somewhere in high school. But this is a consequence of some of this length stuff, which is a consequence of the Pythagorean theorem. And so we can find the distance between any 2 points looking at these kind of ideas here. Right. And the last thing I wanted to mention was a few special vectors. Which we're going to call the elementary vectors. So in R3, the vector I, not to be confused with the complex number I, if you're familiar with complex numbers, that's not what we're talking about. This is the vector 1, 0, 0. J is the vector 0, 1, 0. And K is the vector 0, 0, 1. So very special, geometrically speaking, if we're on the XYZ plane. right there, there's I. Here, that's J. And here we have K. Note that these are unit vectors. Put a little hat on top of them to indicate the fact that they're unit vectors. We have these unit vectors. And one of the nice thing about these is that we can take any vector and in R3 and write it in terms of these special vectors. Specifically, if we had 2, negative 3, 4, we can write that as 2I minus 3J plus 4K. And there's some nice ideas. So if you remember back to these properties, if we write them in this way, then we can take advantage of some of these properties on addition and stuff like that. So that instead of thinking of them as components, we can think of them as addition on these special vectors. And these special vectors, wouldn't be surprising to see that they have special properties. And so we can take advantage of those properties in a way that might not be the same. So we can very easily flow between just the component world and what we call a linear combination, aka taking the vectors and multiplying them by numbers and adding them together, is that we can write them in terms of these special vectors and then take advantage of properties involving these. So, again, that's just another way you might see vectors, either in the videos that we make or in class, or if you're looking at other resources or whatnot, that you should be able to see in order to, depending on what situation you're in. All right, so that's it for this video. See you in the next one.